Module 4. Material Properties and Preparation 4.1 Introduction to Material Properties 4.1.1 Introduction. In this lesson, we will explore the fundamental properties of materials that are crucial in the fields of welding and construction. Understanding these properties is essential for anyone involved in these industries, as they directly influence the performance and reliability of welded structures. We will focus on three key concepts: strength, ductility, and thermal behavior. Each of these properties plays a significant role in determining how materials respond to various stresses and environmental conditions during and after the welding process. The significance of material properties cannot be overstated. For instance, strength determines a material's ability to withstand applied forces without failure, while ductility refers to its capacity to deform under stress without breaking. Thermal behavior, on the other hand, influences how materials react to heat during welding, which can affect the integrity of the weld. By the end of this lesson, learners will have a solid understanding of these properties and their implications for successful welding applications. Strength is a fundamental property that indicates a material's ability to resist deformation and failure under load. It is typically measured in terms of tensile strength, compressive strength, and shear strength. Tensile strength refers to the maximum amount of tensile, pulling, stress that a material can withstand before failure. This property is particularly important in welding, as the welded joint must be able to support the loads applied to the structure. In practical applications, the strength of a material can be influenced by several factors, including its composition, microstructure, and the presence of any defects. For example, steel, which is commonly used in construction, can have varying strength levels depending on its alloying elements and heat treatment processes. Understanding these variations is crucial for selecting the right material for specific welding projects. Moreover, the strength of a welded joint can be affected by the welding process itself. Different welding techniques, such as MIG, TIG, or stick welding, can produce joints with varying strength characteristics. It is essential to choose the appropriate welding method based on the material's properties and the intended application. Key points to remember about strength include: tensile strength is critical for load-bearing applications. Material composition and processing affect strength. Welding techniques can influence joint strength. In summary, strength is a vital property that must be carefully considered when selecting materials for welding. A thorough understanding of how different materials behave under stress will lead to better decision-making in construction and welding projects. Ductility is another essential property that describes a material's ability to deform plastically before fracturing. This characteristic is particularly important in welding, as it allows materials to absorb energy and undergo significant deformation without breaking. Ductile materials can be stretched or shaped, making them ideal for applications where flexibility and resilience are required. In welding, ductility is crucial for ensuring that welded joints can withstand dynamic loads and thermal stresses. For instance, if a welded structure experiences sudden impacts or temperature fluctuations, ductile materials can deform rather than fail catastrophically. This property is especially important in industries such as construction and automotive, where safety is paramount. The level of ductility in a material can be influenced by its microstructure and the presence of impurities. For example, materials with a fine-grained structure tend to exhibit higher ductility compared to those with a coarse-grained structure. Additionally, the welding process can affect ductility. Rapid cooling during welding can lead to brittleness in some materials. Key considerations regarding ductility include: ductility allows materials to absorb energy without breaking. Fine-grained structures typically exhibit higher ductility. Welding processes can impact the ductility of the joint. In conclusion, ductility is a critical property that enhances the performance of welded structures. Understanding how to select and manipulate materials with the right ductility can lead to safer and more reliable construction outcomes. Thermal behavior refers to how materials respond to changes in temperature, particularly during the welding process. This property is vital because welding involves the application of heat, which can significantly alter the material's microstructure and mechanical properties. Understanding thermal behavior helps welders anticipate how materials will react during and after welding, ensuring the integrity of the weld. When materials are heated, they expand, and upon cooling, they contract. This thermal expansion and contraction can lead to residual stresses within the welded joint, potentially causing warping or cracking. Different materials have varying coefficients of thermal expansion, which can affect how they behave during welding. For example, aluminum has a higher thermal expansion rate than steel, which can lead to challenges when welding these two materials together. Moreover, the thermal conductivity of a material influences how heat is distributed during the welding process. Materials with high thermal conductivity, like copper, dissipate heat quickly, while those with low thermal conductivity, like stainless steel, retain heat longer. This difference can impact the cooling rates and, consequently, the microstructure of the weld. Key points regarding thermal behavior include: thermal expansion and contraction can induce residual stresses. Different materials respond differently to heat. Thermal conductivity affects heat distribution during welding. In summary, understanding thermal behavior is essential for successful welding applications. By considering how materials react to heat, welders can make informed decisions that enhance the quality and durability of welded joints. In this lesson, we have explored the fundamental material properties that are critical in welding and construction: strength, ductility, and thermal behavior. Each of these properties plays a significant role in determining how materials perform under various conditions, and understanding them is essential for anyone involved in welding projects. We have learned that strength is vital for ensuring that welded joints can withstand applied loads, while ductility allows materials to absorb energy and deform without breaking. Additionally, thermal behavior influences how materials react to heat during welding, which can affect the integrity of the weld. By applying this knowledge, learners can make better material selections and welding decisions, ultimately leading to safer and more reliable constructions. As you move forward, consider how these properties interact in real-world applications and how they can be leveraged to improve welding outcomes. 4.2 Understanding Metal Characteristics 4.2.1 Introduction Understanding the unique characteristics of metals is crucial for anyone involved in welding and construction. This lesson will delve into the properties of commonly used metals such as steel, aluminum, and various alloys. By exploring these materials, learners will gain insights into how their structures influence welding performance and overall reliability in construction applications. The significance of this knowledge cannot be overstated, as it directly impacts the quality and durability of welded joints, which are fundamental to the integrity of any construction project. In this lesson, we will cover the essential attributes of these metals, including their mechanical properties, thermal behavior, and how these factors affect their usability in welding. By the end of this lesson, learners will be equipped with a deeper understanding of metal characteristics, enabling them to make informed decisions in their welding practices and material selections. Steel is one of the most widely used metals in construction and welding due to its exceptional strength and versatility. It is an alloy primarily composed of iron and carbon, with varying amounts of other elements that can enhance its properties. The structure of steel can be altered through processes such as heat treatment, which affects its hardness, ductility, and tensile strength. For instance, carbon steel, which contains a higher percentage of carbon, is known for its high strength but lower ductility compared to low-carbon steel, which is more malleable and easier to weld. The mechanical properties of steel are critical in determining its performance in welding applications. When welding steel, it is essential to consider factors such as the heat-affected zone, HAZ, which can alter the material's properties due to the heat generated during the welding process. Proper selection of welding techniques and filler materials can mitigate issues such as cracking and distortion, ensuring a strong and reliable weld. Additionally, the thermal conductivity of steel plays a significant role in how heat is distributed during welding, influencing the cooling rates and ultimately the microstructure of the weld. In practical applications, steel is used in various forms, including structural beams, plates, and pipes. Each form has specific characteristics that make it suitable for different welding techniques. For example, thicker steel plates may require preheating to prevent cracking, while thinner sections can be welded using faster techniques to minimize distortion. Understanding these nuances is vital for achieving high-quality welds in steel construction projects. Key points to remember about steel characteristics include, high strength and versatility make it a preferred choice in construction. Mechanical properties can be altered through heat treatment. Proper welding techniques are essential to prevent issues like cracking and distortion. Aluminum is another metal commonly used in welding and construction, known for its lightweight and corrosion-resistant properties. Unlike steel, aluminum has a lower density, making it an ideal choice for applications where weight is a critical factor, such as in aerospace and automotive industries. The structure of aluminum is primarily composed of aluminum oxide, which forms a protective layer that enhances its resistance to corrosion. However, this oxide layer can pose challenges during welding, as it must be removed to ensure a strong bond between the materials. The mechanical properties of aluminum vary significantly depending on its alloy composition. For example, 6061 aluminum is a popular choice for structural applications due to its good weldability and strength, while 7075 aluminum, known for its high strength-to-weight ratio, is often used in aerospace applications. Understanding the specific alloy being used is crucial for selecting the appropriate welding technique and filler material. Aluminum can be welded using various methods, including MIG and TIG welding, each offering different advantages depending on the application. In terms of thermal behavior, aluminum has a high thermal conductivity, which allows for rapid heat dissipation during welding. This characteristic can lead to challenges such as warping or distortion if not managed properly. Welders must be aware of the cooling rates and adjust their techniques accordingly to maintain the integrity of the welded joint. Additionally, aluminum's lower melting point compared to steel necessitates careful control of the welding parameters to avoid overheating and burn-through. Key points to remember about aluminum characteristics include, lightweight and corrosion-resistant, making it suitable for various applications. Alloy composition significantly affects mechanical properties and weldability. High thermal conductivity requires careful management during welding to prevent distortion. Alloys are materials composed of two or more elements, with at least one being a metal. They are engineered to enhance specific properties, making them suitable for various applications in welding and construction. Common examples of alloys include stainless steel, bronze, and brass, each offering unique characteristics that can improve performance in specific environments. For instance, stainless steel is known for its excellent corrosion resistance, making it ideal for applications in harsh environments, such as marine or chemical processing. The structure of alloys can significantly influence their welding behavior. For example, the presence of different elements can alter the melting point, thermal conductivity, and mechanical properties of the base metal. Understanding these changes is essential for selecting the right welding process and filler material. In some cases, preheating may be required to ensure proper fusion and prevent cracking, especially in high-strength alloys. In practical applications, the choice of alloy can impact the overall reliability and durability of welded structures. For example, using a corrosion-resistant alloy in a marine environment can extend the lifespan of the structure, reducing maintenance costs over time. However, welders must also be aware of the potential challenges associated with welding alloys, such as the risk of hot cracking or the formation of undesirable microstructures in the weld. Key points to remember about alloy characteristics include: alloys are engineered to enhance specific properties for various applications. The structure of alloys influences their welding behavior and requirements. Proper selection of welding processes is crucial for achieving reliable and durable welds. In conclusion, understanding the unique characteristics of metals such as steel, aluminum, and alloys is essential for successful welding and construction practices. Each metal has distinct properties that influence its performance in welding applications, from mechanical strength to thermal behavior. By grasping these concepts, learners can make informed decisions regarding material selection and welding techniques, ultimately leading to higher quality and more reliable welded structures. As you continue your journey in welding and construction, remember to consider the specific attributes of the metals you work with. This knowledge will not only enhance your skills but also contribute to the overall success of your projects. Embrace the complexities of metal characteristics, and apply this understanding to achieve excellence in your welding endeavors. 4.3 Criteria for Material Selection 4.3.1 Introduction in the field of welding. Selecting the appropriate materials is crucial for ensuring the integrity and longevity of the final product. This lesson, Criteria for Material Selection, delves into the various factors that influence material choice in welding projects. Understanding these criteria not only aids in achieving optimal performance but also ensures that the materials used are cost-effective and suitable for the intended application. Throughout this lesson, we will explore essential aspects such as cost considerations, durability, compatibility with other materials, and performance under different environmental conditions. By the end of this lesson, learners will have a comprehensive understanding of how to evaluate materials effectively, which is a vital skill for any welding professional. Cost is often one of the primary factors influencing material selection in welding projects. It encompasses not only the initial purchase price of the materials but also the long-term costs associated with maintenance, repair, and replacement. When evaluating materials, it is essential to consider the total cost of ownership, which includes initial costs, the upfront price of the material, life cycle costs, expenses related to maintenance and potential replacements over time, operational costs, costs incurred during the welding process, including energy consumption and labor. For instance, while a high-strength steel may have a higher initial cost, its durability and lower maintenance needs could result in lower life cycle costs compared to a cheaper, less durable option. Therefore, a thorough cost analysis is vital to ensure that the selected material aligns with the project's budget while meeting performance requirements. Additionally, it is important to consider the availability of materials, as sourcing costs can vary significantly based on location and market conditions. Durability is another critical criterion in material selection, particularly in welding applications where materials are subjected to various stresses and environmental conditions. The ability of a material to withstand wear, pressure, and corrosion directly impacts the longevity of the welded structure. Key factors to consider include mechanical properties, strength, toughness, and fatigue resistance are essential for ensuring that the material can endure operational stresses. Corrosion resistance. Materials exposed to harsh environments must resist corrosion to maintain structural integrity. Thermal stability. The ability of a material to maintain its properties at elevated temperatures is crucial in applications involving heat. For example, stainless steel is often chosen for its excellent corrosion resistance and durability in marine environments, while aluminum may be preferred for its lightweight and good thermal conductivity in aerospace applications. Understanding the specific demands of the application helps in selecting materials that will perform reliably over time, reducing the risk of failure and associated costs. Compatibility with other materials is a vital consideration in welding projects, as the interaction between different materials can significantly affect the quality and performance of the weld. Factors to consider include welding techniques. Different materials require specific welding methods, such as MIG, TIG, or stick welding, which can influence the choice of materials. Thermal expansion. Materials with differing coefficients of thermal expansion can lead to stress and cracking in welded joints. Chemical compatibility. The potential for chemical reactions between materials during welding must be assessed to avoid compromising the weld quality. For instance, when welding dissimilar metals, such as aluminum to steel, it is crucial to use appropriate filler materials and techniques to ensure a strong bond. Additionally, understanding the metallurgical properties of the materials involved can help prevent issues such as embrittlement or distortion during the welding process. By carefully evaluating compatibility, welders can achieve high-quality joints that meet the required specifications. In conclusion, the selection of materials for welding projects is a multifaceted process that requires careful consideration of various criteria. Cost, durability, compatibility, and performance under environmental conditions are all essential factors that influence the final decision. By understanding these criteria, welding professionals can make informed choices that enhance the quality and longevity of their work. As you move forward in your welding career, remember to apply the knowledge gained in this lesson to evaluate materials effectively. This skill will not only improve your project outcomes but also contribute to the overall success of your welding endeavors. Always keep in mind the importance of selecting the right materials to ensure safety, efficiency, and durability in your projects. 4.4 Surface Preparation and Contaminant Removal 4.4.1 Introduction. Surface preparation is a critical step in the welding process that significantly influences the quality and integrity of the final weld. This lesson will delve into the various methods and best practices for preparing metal surfaces prior to welding, emphasizing the importance of cleanliness and proper treatment of surfaces. Understanding how to effectively remove contaminants and prepare surfaces can lead to stronger, more reliable welds, which is essential in construction and manufacturing industries. In this lesson, we will explore different cleaning techniques, the removal of oxides and other contaminants, and how these practices impact weld quality. By the end of this lesson, learners will have a comprehensive understanding of surface preparation and its vital role in achieving successful welding outcomes. Cleaning techniques are fundamental to ensuring that metal surfaces are adequately prepared for welding. The presence of contaminants such as dirt, grease, oil, and rust can severely compromise the quality of a weld. Therefore, it is essential to employ effective cleaning methods to achieve a clean surface. Common cleaning techniques include mechanical cleaning, chemical cleaning, and abrasive cleaning. Mechanical cleaning involves the use of tools such as wire brushes, grinders, and sanders to physically remove contaminants from the surface. This method is effective for removing rust and scale but may not be sufficient for oils and greases. Chemical cleaning, on the other hand, utilizes solvents and degreasers to dissolve contaminants. This method is particularly useful for removing oils and other residues that mechanical cleaning may leave behind. Abrasive cleaning combines both mechanical and chemical methods, often using abrasive pads or media to scrub the surface while applying a cleaning solution. It is important to select the appropriate cleaning method based on the type of contaminants present and the material being welded. For instance, aluminum surfaces may require different cleaning techniques compared to steel due to their unique properties. Additionally, the choice of cleaning method can affect the surface finish, which in turn influences the weld quality. Key points to remember include: always assess the type of contaminants before selecting a cleaning method. Ensure that the cleaning process does not damage the base material. Follow safety protocols when using chemical cleaners to avoid health hazards. In summary, effective cleaning techniques are essential for preparing metal surfaces for welding, and understanding the strengths and limitations of each method is crucial for achieving optimal results. Oxides and other contaminants can form on metal surfaces due to exposure to air and moisture, leading to issues such as porosity and weak welds. The removal of these oxides is a critical aspect of surface preparation. Oxides can be particularly problematic when welding materials like aluminum and stainless steel, which are prone to oxidation. One effective method for removing oxides is the use of chemical etchants, which can dissolve the oxide layer without damaging the underlying metal. For example, a solution of phosphoric acid can be used to treat steel surfaces, effectively removing rust and scale. Another method is mechanical abrasion, which involves using tools like grinders or sanders to physically remove the oxide layer. However, care must be taken to avoid excessive abrasion that could alter the surface profile. In addition to chemical and mechanical methods, thermal cleaning techniques can also be employed. This involves heating the metal surface to a temperature that causes the oxides to break down and be easily removed. This method is particularly useful for large components that cannot be easily cleaned using traditional methods. It is essential to ensure that all oxides and contaminants are removed before welding, as any remaining particles can lead to defects in the weld. Key considerations include: always inspect the surface after cleaning to ensure all contaminants are removed. Use appropriate personal protective equipment, PPE, when handling chemicals or performing mechanical cleaning. Understand the specific requirements for the material being welded to select the best removal method. In conclusion, the removal of oxides and contaminants is a vital step in surface preparation that directly impacts the quality of the weld. Employing the right techniques will help ensure a clean and reliable weld. The quality of a weld is heavily influenced by the preparation of the metal surfaces involved. Proper surface preparation not only enhances the aesthetic appearance of the weld but also ensures its structural integrity. A clean and well-prepared surface allows for better fusion between the base metals, reducing the likelihood of defects such as porosity, inclusions, and weak joints. When surfaces are contaminated, the weld may not penetrate adequately, leading to weak spots that can compromise the overall strength of the structure. For instance, if oil or grease is present, it can vaporize during the welding process, creating gas pockets that weaken the weld. Similarly, oxides can prevent proper bonding between the metals, resulting in a poor quality weld that may fail under stress. Moreover, the impact of surface preparation extends beyond the immediate quality of the weld. It can also affect the long-term performance of the welded joint. Welds that are not properly prepared may be more susceptible to corrosion and fatigue, leading to premature failure in service. Therefore, investing time and effort into surface preparation is crucial for ensuring the longevity and reliability of welded structures. To summarize the impact of surface preparation on weld quality, clean surfaces promote better fusion and reduce the risk of defects. Contaminants can lead to weak welds and structural failures. Proper preparation enhances the durability and performance of welded joints. In conclusion, the significance of surface preparation cannot be overstated. It is a foundational step that lays the groundwork for successful welding outcomes, ensuring that the final product meets the required standards of quality and reliability. In this lesson, we have explored the essential methods and best practices for preparing metal surfaces prior to welding. We discussed various cleaning techniques, the importance of removing oxides and contaminants, and how these practices directly impact weld quality. Understanding these concepts is vital for anyone involved in welding, as they play a crucial role in achieving strong and reliable welds. As you move forward, remember that effective surface preparation is not just a preliminary step, it is a critical component of the welding process that can significantly influence the success of your projects. By applying the knowledge gained in this lesson, you will be better equipped to ensure that your welding surfaces are properly prepared, leading to high-quality and durable welds. 4.5 Handling and Pre-welding Processes 4.5.1 Introduction. In this lesson, we will focus on the essential aspects of handling and pre-welding processes that are critical for ensuring the safety and quality of welding projects. Proper handling and storage of materials, as well as effective pre-welding procedures, are vital to achieving durable and high-quality welds. Understanding these processes not only enhances the overall efficiency of welding operations but also minimizes the risk of defects and failures in the final product. We will explore various protocols and best practices that should be followed during the handling and storage of materials. Additionally, we will discuss the importance of pre-welding processes, including inspection and preparation, which play a significant role in the success of welding applications. By the end of this lesson, you will have a comprehensive understanding of how to manage materials effectively to meet safety standards and ensure readiness for welding. Safe handling of materials is a fundamental aspect of welding that cannot be overlooked. It involves the proper techniques and precautions taken to prevent accidents and injuries during the transportation and manipulation of materials. Key considerations include personal protective equipment, PPE. Always wear appropriate PPE such as gloves, safety glasses, and steel-toed boots to protect against potential hazards. Proper lifting techniques. Use correct lifting techniques to avoid strain injuries. When lifting heavy materials, bend at the knees and keep the load close to your body. Material storage. Store materials in a designated area that is clean and free from obstructions. Ensure that materials are stacked securely to prevent tipping or falling. In addition to these practices, it is essential to be aware of the specific properties of the materials being handled. For instance, some metals may have sharp edges or may be prone to corrosion if not stored properly. Understanding these characteristics can help in implementing effective handling strategies. Furthermore, Training workers on safe handling procedures is crucial to fostering a culture of safety within the workplace. By prioritizing safe handling practices, we can significantly reduce the risk of accidents and ensure a safer working environment. The storage of materials is equally important as their handling. Proper storage protocols help maintain the integrity of materials and prevent contamination or damage. Here are some key storage practices. Environmental control. Store materials in a controlled environment to prevent exposure to moisture, extreme temperatures, or harmful chemicals that could affect their properties. Labeling and organization. Clearly label all materials and organize them in a manner that allows for easy access and identification. This reduces the time spent searching for materials and minimizes the risk of using the wrong type. Regular inspections. Conduct regular inspections of stored materials to check for signs of deterioration or damage. Address any issues promptly to prevent further complications. Implementing these storage protocols not only protects the materials but also enhances the overall efficiency of the welding process. When materials are stored correctly, it ensures that they are ready for use when needed, reducing downtime and improving productivity. Additionally, proper storage can help in maintaining compliance with safety regulations, further emphasizing its importance in welding operations. Pre-welding processes are critical steps that must be undertaken before the actual welding begins. These processes ensure that the materials are adequately prepared and that the welding environment is conducive to achieving high-quality welds. Key pre-welding processes include surface preparation. Clean the surfaces of the materials to remove any contaminants such as oil, grease, rust, or paint. This can be achieved through various methods such as grinding, sanding, or using chemical cleaners. Fit-up inspection. Check the fit-up of the materials to ensure that they align correctly. Proper fit-up is essential for achieving uniform welds and preventing defects. Preheating. In some cases, preheating the materials may be necessary to reduce the risk of cracking and improve weld quality. This is particularly important for thicker materials or those that are prone to thermal stress. By following these pre-welding processes, welders can significantly enhance the quality and reliability of their welds. It is important to recognize that neglecting these steps can lead to various issues, including weak welds, increased likelihood of defects, and overall project failure. Therefore, investing time and effort into proper pre-welding procedures is crucial for successful welding outcomes. In conclusion, the handling and pre-welding processes are integral components of successful welding operations. By adhering to safe handling practices, implementing effective storage protocols, and conducting thorough pre-welding processes, welders can ensure that materials are managed properly and that the welding environment is optimized for quality results. As you move forward, remember the importance of these practices in your welding projects. Applying the knowledge gained in this lesson will not only enhance your skills but also contribute to the overall safety and efficiency of your work. Embrace these protocols as part of your routine to achieve durable and high-quality welds.